All right. So today we will work on data. There is a signal, right? Signal is a carrier that can carry your data, and there is no guided media because signals is radiating from the antenna. There are two types of antennas, basically, right? Some antenna can radiate the signals 360 degree, but some directional. It doesn't matter. We don't care here in wireless network. But that is too much device oriented. And there's a data rates. When you say data rates, usually how many bits that can be transmitted per second. While we have data elements, we also have signal elements. Signal usually generated by a device. If you have a cell phone, then cell phone generates signals. To the signal, you can send data of texting, your voice, email, or any data generated from applications, right? And there is also signal rates or modulation rates. What that means is that signal elements per second. We call that baud rate, the rate at which signal elements are transmitted. And there is a polar system applied, unipolar, and then polarized. Unipolar, then all the data that can be generated from your device for wireless communications have the same sign. What that means is that your device generates from 0 volt to 1 volt, 5 volt, 10 volt, 15 volts, all positive voltages, then that is unipolar system. If it is polar, then positive and negative. One logic state represented by positive voltage, the other by negative voltages, right? I guess you guys are doing something else, something urgent or some other course project due soon by tonight. I don't know, it's so many noises from among students. We're talking about something else. Okay. Data encoding techniques can be categorized in this way. We have digital data, analog data, and digital signal and analog signals, right? Actually, two types of data and two types of signals. If we mix them completely, then 2 by 2, which is four possible cases. But in this slide, we do not talk about analog data over analog signals. Analog data over analog signals, usually that is typical phone systems. An old cell phone, not the digital cell phone, not the cell phone over 2.5G or 3 or LTE, but 1G, for example. Then our voice is analog, and phone has analog signals. We are not although talking about cellular signals here, we are talking about Wi-Fi. I mean, right now it's not really Wi-Fi. Yeah, another module that we may enter into today is Wi-Fi. So these techniques, whatever we are saying on this module is applied to all cellular, Wi-Fi, or any additional 802 dot something, 11, 15, or even GPS signals, right? Was something that we looked at but not really exercised was LED communications that we will do later. So out of 4 possible combinations, we're going to look at 3. Digital data over analog signals. Digital data over analog signals. Digital data over digital signals. And analog data over digital signals. Usually, I mean, current wireless network, Wi-Fi, for example, that is digital data over digital signals. It's not a problem, right? So techniques well known so far. For example, modem. Then modem is the device that can handle digital data over analog signals. And wired LAN, like Ethernet, then digital data over digital signals. Codec. Many of the multimedia data sources need codify and decodify. So analog data over digital signals. For example, if we have movies on CD-ROM drive, then CD-ROM drive is digital signals, but movies itself is analog data. So that is a codec. Algorithms and techniques have been used. Any comments, Talib? So today we're going to look at digital data over digital signals. So digital signal is a sequence of discrete, discontinuous voltage pulse. It is a pulse, like a step function, right? Pulse is usually a step function. So that we have a pulse like this. So we have one high voltage here, and then low voltage here. And there is also the wavelength from here to there, right? There is one cycle. There's a wavelength. And period means the time at which one cycle of a signal can take place. Usually a pulse can be triggered by a system clock. System clock on your device. Okay. If you're working on Wi-Fi from your laptop, then laptop has a system clock. Okay. It should be also synchronized. bit duration, that is the time it takes for the transmission to emit the bit duration. So in the digital data communication, there are issues that we always consider is these issues: bit timing, recovery from signals after we do modulates, and then noisy, a lot of interferences. More interference occur in wireless communication. So this is one of the major issues. Before we do, we need to talk about encoding technique today. Why do we need to encode? Back to our original issue of wireless communication. David, of course, right. You have data right now with you. How can you send the data to your destination? Then you need to have a carrier that can carry your data, right? And there is no guided media. There's no Ethernet line, but it is radiated in the air, right? So first of all, power is important. If we have a big power to radiate signals, then it can reach further. If we have very low power, then signal does not reach further, right? And also, over the course of that signal propagates, there may be some obstacles, right? That obstacle may be absorb the signal, then it cannot penetrate. Or some signals maybe hit the ground. Some ground may reflect it. Some signals directly reach the destination. Some other piece of data, signal, reflects and arrive at the destination with some time delay. The very same data can arrive, but repeatedly, like echo in our acoustic voice. If you say some, then, for example, I can tell Talib in some valley, Afghanistan, a lot of echo. I can tell him so that he can hear my voice directly. And then a second later, there's another voice that comes to his ears by reflecting at some points, and more and more and more, right? The exact same thing can occur. They are all noisy. How can we filter that out, right? Strength is not the same. Some signal strength may be attenuated dramatically or slowly. A lot of. I think Talib wants to say something. He wants to say something.
Yeah, I just had a question about if it's low frequency or high frequency. That being
Oh, you missed a lot. That's the view. We talked about the frequencies a lot. That affects data rates, frequencies. For you to catch up a little bit, there's a lot of frequencies, and we are now talking about, for example, microwave, where there is a cell phone and then Wi-Fi, 802.11, they're all here. So we are talking about somewhere here in this frequency, right? Frequency, some gigabytes, right? 2.4 gigabytes or 5 gigabytes. That is the frequencies. Um,
All of Wi-Fi falls into the microwave band.
yeah, in the same range, same frequency range as microwave. Microwave was uh, it was a byproduct of something else. You know that, right? Historically, uh, the scientists, I mean, engineers didn't plan to make microwave that we are talking about, like warming the food. It was not originally intended, but that is the byproducts when they are working on something else. I forgot what that is. Um, and then our voice is somewhere here in this frequency, for example, 20K hertz, very, very low frequency. And uh, the wireless communication highly widely used right now is the frequency of microwave. And there is a real, real, very high frequencies, which is, for example, X-ray, because that is a high frequency, it can penetrate and affect to us, for example, our human cell can be heated by X-ray because that can penetrate. So it can kill some of our cell, right? If it's a cancer cell, okay, right? But sometimes they can kill cancer and surrounding healthy cells as well. Therefore, X-ray treatment is usually like a accurate spot point, spotted, yeah, localized treatments. A lot higher than that, gamma. There are some techniques used by gamma level frequencies. So the issue here is that if we develop a device that can generate very high frequency, for example, X-ray level frequencies, and communicates, then a lot of things can be communicated very quickly. We cannot imagine that. All of the data so far that we have all over the world can be transmitted quickly. So you can receive all the data. But a lot of side effects, right? So many people may die, killed, if we use the X-ray. The lights that we can see, so that you can see me and I can see you, that is here, visible lights. Here, visible lights wavelength zone, which is about some petahertz. That is our visible, the frequency of the light frequency that we can identify. There's a lot of, I mean, wider range of lights available, but we cannot see it. Our eyes cannot recognize. Our eyes can recognize only that limited, from red to violet. Anything below red, our eyes cannot recognize. We call that infrared. The infrared frequencies. A lot of sensors are functioning in that frequency range. Sensors. We may offer that course. Some of you noticed from the web page there is a new course already developed. I've taught separately multiple times, but not under the new course. I'm not sure how many of you may interested in, but it's called Mobile Technologies and Wireless Sensor Services, which requires a lot of work uh, and time investment. Basically, what we are going to do currently, I'm thinking of I'm going to develop uh, apps development for iPhones. I've talked so many times for apps development for Android, but apps development for iPhones. One requirement for that course is Apple, Apple laptop. Otherwise, you cannot emulate it. Plus the sensors. Sensors are cheap, as you might know, right? All the sensors are so cheap, and we have so many microcontrollers. Not so many, but enough for controllers so that you can use them for free. But anyway, so sensors are here, infrared. So frequency over infrared is already built in so many sensors, right? And and this frequency needs to be received by some of your program if it is developed in this level. For example, cell phone. So sensor generate signals, then your some type of antenna should receive it. That antenna is called XB, right? XB antenna. We are going to do that in our during our tech nights. It's called XB, right? Comes from the animal bees. Bees is not called animal, right? It's insect. Is it insect? What's the bees? Bees falls in what categories? Olivia. Oh, bug. It's a bug.
We just had our house has our business has types of actually.
Oh yeah.
Yeah,
In summer, I got two shots from honey net. It paralyzed me in 10 minutes. So I delivered to the emergency room, and then I got two bottles of Beni, Beni, Benadryl, two bottles of Benadryl. Yeah. Two bottles, just IV bottles. And why are you saying allergy? Honeybee itself has a poison. Anybody okay from poison? Somehow everybody has some issue, right? I may be a little more sensitive than you, but anyway, there's a bee. Uh, if you see bees, raise your hand. You've never seen bees. You've never seen bees? I'll bring next time for you. Bees has antenna. You know that, right? All the bugs, flying bugs has antenna. Not all, but bees has very, very powerful antenna. Bees can communicate for how long the distance? 2 miles. Bees can fly 2 miles from the honey net, the cage, honey cage, and come back. If there is some interference in between, bees cannot come back and then die somewhere. You've seen some honeys, like orphanage honeys. I mean the bees. Sometimes the bees come here in this hallway. That is often is bees. But anyway, bees has very powerful antenna and wireless communication. Bees by nature has only wireless communication, right? Olivia, have you seen any bees the wired communication?
I talked to them.
Wired
She wire
through a wire shock? Okay, so that is a bee. Bee is somewhere here. I think we looked at this page a few times, but this time someone who needs some refreshment or to talib, for example. So you know where we are, right? These are all talking about frequencies in hertz, and then there is a wavelength in angstrom. 1 angstrom is 10 to the negative 10 to the power of negative 8 centimeter, right? Very, very, very tiny, small wave, and something like that. Okay, so what we are going to do is the idea here is this. This type of circuit can generate the signals like sine waves. Okay, if you are interested in, you can build, but we are not interested in. So you can generate this kind of sine waves. And then we might have data like this, X, Y, Z, right? And then we can mix X with some of the data, right? So that is the coding. The coding is that we have signals and we have data. Data needs a signal, so signal can propagate. How data can be encoded with the signal? So one signal, which is a modulated signal, can be radiated and fly to the destination. That is the issue. Techniques that we are going to look at from the very, very basic and simple technique to a little bit of high tech. Little bit. This is a well used, widely used, but not right now. But for example, Manchester. We looked at I and David imitation game. The place there, the location there is Manchester, UK. If anyone remember that, I'm trying to watch that movie more and more and more, so that maybe next week or later after that, each signal needs a preamble signals. We call that preamble the code. Yeah, beginning of that. So if you watch the movie imitation game, then preamble was imitated from dance. Maybe so, right? Some dance. Some dancer explains why she did that, and then the guy immediately got hint and then solved uh, the long-lasting unsolved problems quickly. Abu, you want to say something? Oh, is this your antenna? Okay. So let's see the name first. None return to zero level. This is called the NLGL. NLG, NLZ, L. Zero level. non-return to zero level encoding format. Very similar to that, but little advanced, is non-return to zero interval, NRZI, and bipolar AMI, alternate mark inversion, pseudo ternary, Manchester, the two versions of Manchester code. I think there is a very, very good, strong engineering program at Manchester. Anybody from UK? You? Can you say something about Manchester? Okay. I want to visit Manchester once in my life one time. If I retire, so that I can explain to my students more and better about Manchester code. Okay, so let's take a look at each one of those. To understand that, we have to, for example, this signals, each tick, each pulse here is generated by, see, this is a pulse, right? Typical pulse generated by clock. Clock is ticking. There's a clock speed. Clock can tick, for example, 2 billion times per second. Then our process can be, or our communication rate can be at gigahertz. So gigahertz processor, gigahertz speed of communications. So all determined by primitively the clock. So if we use a high speed clock, then there's a lot of room that we can improve the speed. But anyway, here's my question. If the length of a pulse is 2 milliseconds, which means pulse can the period of pulse is, so one cycle is 2 milliseconds. Then how many pulses per second? I would say it's not wavelength, but maybe period, right? In our terminology that we learned earlier, period of a pulse is 2 milliseconds. Then how many pulses generated per second? 500 pulse. Millisecond, therefore, that is 10 -3 per second, right? 2. But if we use all, then how many such pulse can be generated? 2b and 1 second. 2 milli, it's not per second, 2 milliseconds. Let's see. Erase. I'm going to erase this, right. Pen. So if we multiply it by 500, right? 500, then it'll be in 1 second, right? 2 times 500 is 1000. 1000 times 1 over 1000. Then that is 1, right? So how many pulse? 5 per second. So for example, if we have, this is a second, from 0 to 1 second, pulse can, how many times? 5 times, 500. 500 of these. So maybe this is from here that is 1 millisecond, and from here that is another millisecond. Therefore, this period is 2 milliseconds. If we reach 1 second, then we could have 500 of such. So there's a 500 pulse. For signal elements, because we have one pulse can be one signal element, we cannot divide that pulse. Pulse is the minimum, that is the unit, that is the primitive. So that is one signal element. So we might have 500 signal elements. So 500 signal elements. Again, depending upon the thing that we learned last week, the chipsets for signals. If you use 4 chipsets per signals, 4 chipsets of signal of a channel to represent one data, then you might have 125 data elements can be transmitted per second. But at most, what is the maximum baud rate? Then, oh, I can encode one data per pulse, for example. One data per pulse. Then $500, right? 500 data can be transmitted. That's what we are talking about. So there are many different algorithms. One pulse can have one data by saying that if there is a volt, then we can say data 0. If there is no volt, data 1, for example. In this simple mechanism, then we can send 5 data elements because we have 5 signal elements there. Or to represent 0, 1 data, I need 4 of these. So more accurate. Or you can duplicate. One can appear per pulse so that we can disperse to generate spread spectrum signals, right? Spread spectrum packets. We looked at last week. Okay, then with this primitive, let's take a look each. All right, what is the NRZL stands for? Non-return to 0 level. The idea here is this. I think I've talked about that, right? 0 means high level. This is algorithm, very simple algorithm. 1 means low level. What it does is that your device can generate signals the way the format formalized here. If your device use NRZL, then if there is a 0, and for example, data that you want to send to is converted to the binary code, so it's zeros and ones. So if it is 0, then you send high voltage. If there is 1, then low voltages, right? So on and off. Therefore, let's say we have this. Then there's a low voltage. This is high. We can say this is 5 voltages, and this is 0 voltage, right? Is this unipolar or bipolar encoding? This is unipolar encoding, right? Because we have all the same signals, right? Same sign right now. Because this is a 0, low voltage. Therefore, it is. If you have these signals, then you can. That means 1. If you have 1, then you can make these signals, vice versa, right? So given these signals, then you can interpret it in this way. Given that data, and if I ask you to encode using NRZL, then signal should be in this way. Again, for simplicity, in this lecture, we are using digital signal over digital data over digital signals, right? What is this then? 0. Very simple, right? 1, 1, 0, 0, 1, 0. So far, so easy. So you might say, oh, encoding is so easy. Maybe.
How does the computer know that it's double ones?
Oh, that is a very good question. Therefore, this encoding technique is evolved. So some other techniques tell you. In this no return to 0 level, cannot distinguish. If very longer than, I mean, this is a double longer, maybe okay, but double entry for maybe confused, right? Maybe 31 zeros and 32 zeros. Therefore, they developed. For example, when it comes to Manchester, then can be distinguished. Very good question. You are motivated to the new formats. Okay. No return to 0 inverted. 0 means no transition at the beginning. 1 means transition at the beginning of an interval. Look at the interval this from here there, right? The beginning is here so that you know what it means. Is there any transition? If you see this, there is a transition, right? From low voltages to higher voltages. If there is a transition, then this means what? Number 1. What about this? 0, because there is no transition. If you look here, there is no transition. What about this? There's a 1, because there is a transition. If you look at this, there is a 1. There's a 0, 0, 1, 0. So far, so good. So far, you may say, I like it. So that is that. And bipolar encoding. What we have so far here, that is unipolar, right? Only positive, all negative, there's no sign difference. But if you have a device, then we may want positive 5 voltages, negative 5 voltages, for example, to accommodate, to make our signals more efficiently, effectively generated from our device. Then the algorithm now here is bipolar. Very similar to NLZI, but here we use positive half voltages and negative half voltages rather than 1 volt. Okay, so here's the issue. So example, this is the code 010100. So recall NRGL. If it is 0, then high voltage, 1 low voltage, high voltage, low, high, high, right? It's not a problem. NRGI, if there is a transition at the beginning of that interval, then 1, otherwise 0, right? Is there, oh yeah, there is a 1. So it should be here. Transition, right? From 0 to top, there's a transition. So that should be 1. And there is, in the beginning of this, there is also a transition, so 1. In the beginning of this, there is a transition, therefore 1. Encoding. Let's say we have a pulse, digital signals. I have data, so that how can I encode my data in that pulse signals? Correct. Yeah, same data. This is the same data. For this same data, yeah, how it can be encoded if we use this, if we use that, for example. There's a transition, so it should be 1. See here, there's a transition. Oh, wait a minute. We don't have to say this, right? We start. I'm sorry, yeah. Yeah, we don't have to say. Because I was working on the first. Yeah, I know what you meant. Very good. Let me see, erase this. So we don't have to do this. Yeah, we're not assuming any. What it means is that 0, then there is no transition. 1, there is a transition, so up. 0 means no transition, so continue. 1, there is a transition between this and that, so wait a minute. So there is no transition. But this is not bipolar. Let's see, is it bipolar? No, it is not, right? 0 means no transition, 1 means transition. Therefore, 0 means no transition, 1 means we make transition. Now we do not make transition, right? So we have a transition here. Say this is not necessarily simple thing is this. This is a 0 volt. This is 5 volt, for example. Right. Forget about this line in between. We're not saying this. Okay. Rather than this, let me revise this. Discard. Okay. What we can do, I don't think we need this, right? I'm gonna delete this simply. So as a 1, so there is a transition, and 0, no transition, no transition. Simply like this. Yeah, this is the answer. All right, and bipolar encoding, similar to this, but rather than staying at the same voltage, same signal, same sign the voltage, but we have bi sign the voltages. So 0 means there is no change. 1 means there is a change, transition, but we need to send half voltages, say 2.5 volt. Okay, there is 1. What is, yeah, 0 means 0 volt. 1 means positive or negative half volt. 0 means 0 voltages. So because it is 0, 0, therefore all 0. If there is a 0, then quickly we can make 0 like this. This can be 0, this can be 0. Only the issue here is that if there is a 1, then first one will be positive half voltages, and then second one is negative half voltages. So depending upon the odd number and even numbers, so we have alternatively half voltages. That's what we have bipolar code encoding. So here alternating uh, positive half and positive negative, negative negative half voltage and positive half voltages. If this is 0, then all 0. That's what it is. Okay. And then pseudo ternary. So far a little bit confused, right? Yeah. So every time if you have, yeah, I'm going to ask homework assignments. Therefore, you need to, don't try to do this from top of your brain, but you have to always go back to the sample and then the explanation, and carefully solve the problem. Pseudo ternary. 1 represented by absence of line signal, 0 represented by alternating positive and negative. This is very similar to bipolar. This is another bipolar, but 0 means positive and negative.
So if there's a change, it's similar to like
No, it's quite different. Let me see. This may not be true either, so we have to be very careful. So 0 means positive and negative. 1 means absence of line signals, so there is no signal. 0 means no. Oh, okay, I need to go back. Okay, 1 means no signals. So this should shifted here. 0 means therefore signals. 1 means no signal. 0 means 1 negative, 1 positive. That's what it is, right? Alternating positive and negative. So no advantages or disadvantage over bipolar AMI, which is very similar to this, but not much different. Only difference here is, I'm going to revise this a little bit again, which means this should be positive so that I can move here. 0, 1, 0 positive, and next 0 negative, and 1 remains the same. And then next 0 is again alternatively positive, and then this is negative. Okay. Any question? Oh, this was not changed. Hold on. This shouldn't be. Yeah, right.
Why don't you use bipolar encoding over the CME2? Why would you choose one over the other?
What are the different proposals of encoding techniques? They are similar. So the comment says there's no difference between bipolar, yeah, AMI and pseudo ternary. Right, there's a little bit opposite. Signal, if you see these signals, they are really opposite, right? So one here voltage, here no voltages, but in this case, um, oh, this is bipolar. You should ternary. This is also positive and negative. One positive. If we use one positive here, the next one should be negative. Yeah, one. Yeah, alternatively. Okay. So far maybe okay. A little more things that may make you confused. Here, Manchester, which is a really good technique. Manchester is zero means transition from high to low in the middle of the interval, and one means transition from low to high in the middle of the interval. In this Manchester, for example, uh, distinguish if there is a multiple ones, for example, or multiple zeros. If we have a multiple, I mean, contiguous repetition of the same code using no return zero technique, then we do not know how many it appears, how many ones, right? How many zeros. But this Manchester tells you, for example, zero means high to low, right? This is an interval. So this overlay a little bit of that interval. So if there is a transition from high to low, this means zero. If we have data zero, then we need to generate this kind of signal, right? From low voltage to high voltage, then that is one. Another here, from low voltage to high voltage, then that is one. From low to high, there is another one. From high to low, there is a zero. From low to high, there is one. From low to high, there is one. From high to low, there is a zero. So if we have three triple ones or double ones, still our signal can tell you how many, which is the advantages over non-return, no return, zero encoding techniques, right? So this has advantages. Now, my question back to you. Can anyone see any disadvantages of this Manchester? techniques?
Yes.
What?
Because without the limit that's receiving the signal, you'll be able to tell if there are multiple zeros or multiple ones. Confuse it with ZI or
Right, yeah, there is advantages. What about disadvantages of this Manchester?
the disadvantages of this, if you get, well, it's not a disadvantage because there is a voltage protection. If you get 1, so the voltage keeps increasing, until it gets to be there is.
Okay, can you say it in different way? I know what you mean, but a little bit more.
Okay, so a positive change indicates a 1. By the way, Professor, I'm having a problem with this graph because it doesn't show really 1, because 1 is supposed to go up and then up again.
No, we have a two voltages scale.
Right, so if I'm reading
Do this. I know what you mean. If we have a one source, then we can make this. If we have multiple source, then multiple ones. For example, I have 0, 1, 1, 1 from one source because we have the mix, right? Another, let's say this is your voice signal. Your text signal comes, and your another signals. So at once, multiple signals needs to be modulated together, right? From multiple different sources. In that case, if you have two ones, then you can make this up so that we can tell, oh, that is not, yeah, that is two sources has one. Yeah, things like that.
if we have low voltage with a single amount of time, I can see how many people.
That relate, yeah, and this one disadvantages related to what you're saying. I want to say more nicely, yeah, a little nicer. Beautiful languages or more technical terminologies.
I can see that. I'll try. So I can see that what you're reading is the change.
Right.
So if you don't have a change over a certain amount of time, it may confuse the system because it's expecting to see a change. So again, it seems like you don't have.
No.
So let's say you see.
No, this is change. One means it is not just change. One means from low to high. If you have if you have a series of ones, then all low to right, low to right, low to right. So there is no such, for example, there is no such signals, Talib, like this. There is no signals like this in Manchester. This is not possible. Manchester does not have this signals. Continue, right. There's no such things. Always, yeah, either from top to bottom, top to low, I mean, high to low, or low to high.
So our only question is you have 1 because it's high voltage, right?
Mhm.
And you have another 1 because it's high voltage.
One, because we have a low to high. From low to high, that means one. Think about this.
So you go from high to low.
High to low means there is a zero.
So to get that 1
One again, here, look at this. This is one, low to high. Another one, again, low to high.
that's what I'm saying, but the only way you got from low to high is you have to come down.
Sure, yeah, it should. It should. It's not come down, it's a voltage, it generates, right?
So it went from high,
Right,
it was low to high, you have 1,
right.
and you have another low to high.
Mhm.
When it was just high, it came.
There's no such thing, no continuous high in this Manchester. I think you got some hint of disadvantages. You're trying to say, but not get to that clear points yet. Let me tell you. To make this half and half, then your original source, I mean sound, no, signal element two signal element can represent one data at least, right? Do you see the difference? Previous, one signal element represents one data. One chip per one bit of data. In this case, two chips of signals represent one data. To represent one, you need to have low voltage chip and high voltage chip. Device point of view, there is no transition. It sends low voltage, high voltage, pulse, like low, high, low, high, low, high, low, high, like that. What it does that here in this case then, if you see here, your pulse generates high, low, low, high, low, high, low, high, high, low, low, high, low, high, high, low. That is a sequence of the voltage generation. Okay.
So the disadvantage is you need two chips
At least, yeah.
just for the second.
Just for one data element, you need to have two chips of signal elements. Which means Manchester's ideal case, Manchester, the data rates generated from Manchester encoding techniques is slower than many others so far that we looked at.
The benefit is more accurate.
Exactly. It should be accurate. Accuracy is important, right? Should understand, for example, if there is a 111111111, there's some code, right? So that we can tell. Oh, this means Hi Hitler, for example, from imitation game. There's a preamble, right? Hi Hitler is the preamble of that from the movie. Okay. So change signal level every 1 millisecond. Signaling elements is 1000 pulse per second. What is the data rate? If we use Manchester. So have two of these signals, two elements can hold one data, right? So if you have 1000 pulse of signal can hold how many data sets? 500. So that's 500 what? Bit per second. At most. This Manchester, see here, if you look at clock, then two pulse, say two pulse, can hold one data. Two pulse, right? One data. And one nice thing, one of the big advantages in performance of Manchester is the simple operation. If you use exclusive operation, then you have this quickly. So I think some of you might want to make a Python program to make this. So clock ticks and you send data, then very quickly you can get encoded messages generated from Manchester encoding technique. Thing is this, any text messages, okay, say, hi Hitler, I will kill you. We can convert that in binary, right? Definitely. It's simple to generate binary code. And then your clock generate pulse. 1 0 1 0 1 0 1 0 1 0. And take 1 0. Take 1 first. And exclusive OR with 1. 1 exclusive OR 1 is 0. So this is a 0. And then this is a what? This is a 0, right? 0 exclusive OR 1 means 1. So we have 1. Again, here is 1. 1 exclusive OR 0 means 1. So we have 1 here. 0 exclusive OR 0 means 0. Another pulse. 1 exclusive OR 1 is 0. 0 exclusive 1 is 1. So this Manchester code is very simple to be generated by exclusive OR operation. Now, those who wants to do that, to program this, then you have a series of 1010 like this, right? You can find out the word. You can convert this binary code to the text again. Then there is a completely new text. Although I said, hi Hitler, I will kill you. After you do this Manchester encoding, I don't know what that is, but maybe something, it's not. Let's likely, hi Hitler, I will kill you, that sentence, right? There's some other sentence. Or it is not, it's meaningless. That is really uh, um, like like encoding. What's that? Like it's some cryptography. Yeah, encrypt. Yeah, some of it encrypt so that no one can recognize. Okay. Okay, time 7:41. I know some of you wants to grab some food from the cafeteria before they close. So let's take a break, and when we come back, then it's another version of Manchester. If I continue to do another version of Manchester, then you're totally confused. Finally, I confused everything. All right, so let's take a break. Okay. As we looked at minutes ago, Manchester is good, is accurate. Therefore, it is now being used in RFID and NFC to collect your money, right, for toll payment. As it says, it was originally developed by the University of Manchester at UK. It's very simple, right? Very simple to generate the Manchester code, and also very quickly because we are using exclusive OR operator. And given, see here, data can be any text, any message, can be converted into binary. And then coding itself is very simple using this to generate another binary, right? This is a binary, another binary. That is encoded binary. This binary is now converted to text. Then we have two text. This text is not the same as that text, right? If you modify the technique here, exclusive OR a little bit more, then you might have a very, very, very good encryption algorithms if you want to develop, right? The coding, the programming of this is very simple, very, very, very simple, but outcome is very, very interesting. Okay, if you want to be hired by some companies like NSA, I want you to try this and make a good demonstration about that, right? Or to Lockheed Martin, if you want. Two means which one? Correct. Two text, yeah. Totally different. Very easily. Yeah, make another exclusive OR. Then you can come back to here. That is all. Whatever we do in exclusive OR, to make another exclusive OR, you need to have this clock. Again, then quickly going back to the original text. No, no, it's not converting from clock to data. It's a modulate data over clock. Or totally different from the earlier encoding techniques. And there is another version of a Manchester. Knowing this, then another version is it's called the differential Manchester encoding. One is represented if transition. 0 is represented by following the previous bit. What it does is that I know Talib was questioning about so many. For example, if you have multiple ones, then multiple low to high, low to high, low to high, low to high. A lot of radical transition over voltages. So he's worrying about the device heat, for example, right? To avoid that, what is the algorithm? What is the resolution here? If there is a repetition, then make it 0. Here, following the previous bits, as far as it follows the previous bit, then encode it 0. For example, 1, 1, 1, 1, 1. The first one is representing the transition. From second remains the same from the previous. Okay, here is a little bit of a modification. So we have a clock, 2 chips per data elements. Let's say we have data 101, something like this. And then differential Manchester here is that if there is a 1, it represents transition, right? So there's a transition. If there is a transition, that it means 1. Okay, so whatever that is, it is 1 because there is a transition. And 0 means repeat this, same form. Same form repeats. If it is 1, then change the face. If it comes from high to low, then another 1 means just transition. If it is high to low, then transition is low to high. If the previous is low to high, and now transition, then high to low. So 1 means we change the phase, because so far we do high to low, therefore low to high. 0 means we repeat, low to high. 0 means repeat. And 1 means change. Whatever it is, we change it. Because it was low to high, now high to low. Another low, then we change it, low to high. Another one, change it, high to low. High to low. Another 0, repeat it. Follow the previous. 0, repeat it. When it comes to 1, change. So entire this tells, we can see quick, apparently this is 1, this is 0, right? It does very similar to Manchester, but if it has a multiple repetition, then same pulse. Low to high, low to high, low to high. We don't have to shift the phase. That is our advantages. Mechanical advantage.
In this case, you can find the differential Manchester just based on the data. You don't care.
Right. We don't care. Right. Based on data. So drawback of this is that the first bit is missed, then completely wrong after that. So first bit is very, very important. In other words, if a signal dropped, first bit dropped, then all confused. If preamble is if you interpret preamble 1 bit longer, then completely wrong. Whole entire, yeah. That is the drawback. It's a drawback, but always we can use it, right? If we send this across our enemies to the other side of our team, so there's always possibility that can be extracted by the enemies using this. So once they miss, their interpretation is totally wrong. So it's a little bit of the modifications. Therefore, you can release wrong message to your enemies. Very, very easily, it can be a wrong message to your enemies. So this type of Manchester encoding and differential encoding probably migrated from the World War II imitation game. They still have strength in this encoding techniques. What I will do, I'm going to give you homework assignments of this. I'm going to post this so you can practice it at home. Okay. All right. It's a good. It's fun, right? Fun. Okay, wireless LAN. Now from this time, we'll look at Wi-Fi, widely used wireless communication. And after we'll look at the technique of Wi-Fi, followed by cryptography of Wi-Fi. And after that, we'll switch gear to cell signals, cell communications, cellular phone communications. And then followed by the cryptography of cellular phone. And then a little bit of a few other techniques, for example, GPS signals and Zigbee, XBee signals. They're all Wi-Fi, all wireless networks. So we look at a little bit of a few other techniques, okay? Not in great detail. Around that time, then it'll be a tech night. So tech night, we already one lab that I introduced to you but didn't do, which was LED communication. So today you will do, if we get to that point, then you will see Wi-Fi network. So your laptop can set up wireless LAN. We will set up access points over your Windows systems over Linux, but because we do not have it. Well, I think we will do it at Tech Nights, right? So some students can work on Linux operating systems. Some students can work on Windows systems to set up access points, and then another laptop can access yours, that access points. And then what you can do is several things that you can do. First of all, using Wi-Fi, you can, no, using Wireshark, you can find out how your device, your laptop, technically it is called the station in Wi-Fi. Your station can talk to access point for Wi-Fi communication, right? Then you can, well, two laptop. One laptop has an access point, another laptop just a station. Two laptop turn on Wireshark together and see the signals from the top, from the laptop with the access points running. You can see some distribution messages. Usually access point to say that access point to first to send out the beacon signals, meaning that access point says to each station, I am here, I am doing routing of your wireless network, wireless connections. So that is distributed. So I want you to take a look at from Wireshark. And from your Wireshark of your station laptop, then your station laptop needs to respond to that beacon signals. Okay, so that your laptop can associate in that wireless network. So those things very interesting, can be exercised. For those who are interested in the programming, then rather than using Wireshark, you can do a Python program to capture Wi-Fi communications step by step. Okay. But anyway, to do that, so Wi-Fi, wireless Wi-Fi, wireless LAN, so-called Wi-Fi, using radio frequency technologies. Radio frequency is a little bit lower than microwave frequency, but it's interchangeably used. Microwave frequency and the radio frequency. Radio, I mean, strictly speaking, radio frequency is lower than microwave frequency. LANs transmit and receives data over the air, minimizing the need for wired connections. So let's say here we have analog signals. Right, this is analog signals. Digital signals, usually that comes from the pulse. But if you have a signal, digital data, therefore modulated digital signal is this. See here we have a 1 0 1 0, whatever that encoded that we obtained from those like encoding techniques, Manchester or differential Manchester. But anyway, outcome of that is this, right? But anyway, so bit stream, that may be the data. So by modulating these two digital signal or analog signal, so that we have a packets. Each packet has header, body, header, body, header, body, that repetition, header and body and header and body, right? But if they are continually mixed together, then it's very hard to identify this is a new header and body. This is a new packet. Identification of a new packet is not really simple. So what they do usually, they allocate the preamble bits or bytes in front, between the packets. So by looking at that, for example, in the movie Imitation Game, the preamble is Hi Hitler. So whenever the code shows Hi Hitler, then simply say, oh, new packet will come after that. Therefore, they can focus it. If they do not identify preamble, then what happens? Everything is scrambled. Like that, we looked at the differential Manchester encoding. If we lose first bit, then all scrambled. You will never know, right? Up to this point, modulation remains the same, either wired or wireless. If we have this signal, then generates the bit streams and send it over the antenna, then that is wireless. If we slide it into the Ethernet, then that is 802.3 Ethernet communication. So packets, this is a packet. Packet is traversing from sender side to the receiver side. So this technique will be learned from network. Network 1, network 2, right? Sender send through the antenna, right? It's the antenna. Therefore, it can be captured by receiver side antenna. Of course, there are a lot of issues, right? So we will look at that. LAN, wireless LAN, WLAN. There's two, actually, yeah, two models. Infrastructure networking or ad hoc networking. Ad hoc, then there's no fixed coordinator, fixed access points. There's no fixed routing. There's no fixed origin and destinations. All flexible, peer-to-peer networking. Easy to deploy and is ideal for small offices. Able to share files, print with the other wireless computers that are within range and in your wireless workload. That is ad hoc networking. Infrastructure networking. The key difference between the structured wireless network and ad hoc is the addition of one extra element, which is access points. If we have access points, then it's infrastructure network. Unlike peer-to-peer networking, structured network computer communicate with each other through the dedicated access points. See here, dedicated access points. Peer-to-peer, one time you can do router, at another time you can be just end node. We can practice that using XB. And the data can be seen by Android microcontroller. Android microcontroller is a device that can set up the communication very easily for another protocol, 802.15.4, which is a little different from this, but frequency-wise, it remains the same frequency range, 2.4 gigahertz. Okay, so Wi-Fi. What is Wi-Fi? Wi-Fi is almost all wireless LANs over 802.11 standards, protocols. Competing technologies, for example, HyperLAN, cannot compete on volume and cost. We don't have to worry about that. 802.11 is also known as Wi-Fi, which is from wireless fidelity. Fidelity means compatibility between wireless equipments from different manufacturers. Wi-Fi Alliance is non-profit organization that does compatibility testing. You can find a lot of regulations from this website, wifi.org. So 802.11 is a standard created in 1997. 802.11b, high rate standard rectified in 1999, allows 11 megabps. So let's compare the 802.11 802.11 standards compared with ISO OSI 7-layer. IEEE is in another layer. If you look at the 7-layer from application to physical, concern in IEEE 802.11 is the little bit of a data link and physical layer. So half of the data link is called media access control, so-called MAC, and physical layer. So MAC layer and physical layer, those two layers are standardized for 802.11. So what we can do here, for all other presentation and sessions, they are similarly available, but major difference between typical wired and wireless 802.11 is the MAC layer and physical layer. Physical layer, definitely, because there is no guided communication, quite different. Media access, so all mobilized. Station is mobilized. It's not one fixed linked to the end of this line, right? There's no line. There's no media. So media access control is the key technique that we need to look at. So first we look at medium access control. Wireless is a shared medium. Air is air. I cannot say, this is my air. Transmitters, there's a lot of interference because it is already shared. Collision again. So what type of collision that we are thinking? We'll look at that, right? Collision means two packets collide with each other. In what scenario? So we'll look at that. So there's a collision detection and collision avoidance. Two types of mechanism available. But collision detection in Ethernet. networking is feasible and widely used, meaning that if data packets collide, then from your receiver side, you can re-request to the sender side. Then you can re-request. Sometimes, depending upon TCP or UDP, but anyway, you can request the same messages. Emails, definitely, the receiver side should request for resending if there is any collision occurs in the middle. So collision is very, very feasible if it is wired communication. In wireless communication, for example, your phone receives something, but there is some packets collided. You detect it. What should we do? Can you re-request? You may, but it's less likely possible because everything is moving. Right, we don't need, yeah. Therefore, what instead of collision detection, collision avoidance is more feasible in wireless communication. Let's avoid it. Usually, two packets are collided with each other. Two packets together, which is distance mark. So collision occurs here. To avoid, so it is detected. What happens then? Hey, listen. Hey, listen. Still another collision. Another collision. Another collision. Another collision. Right. That's possible. So avoidance is better. What they do is, before they send, are you okay? Are you okay? You get to send? Make sure it's clear and send. One is, this guy already said, oh, clear, ready to send. And this guy knows that he is going to receive. Therefore, if somebody says, to me to send, that time will be tested to receive it, and this guy said, wait. So in wireless communication, wait. There's a lot of weight. A lot of weight needed in wireless communication. Weight is backup. If we have so many different sources, senders, to send the data to me, then I can say, oh, now we talk. And all others wait. You back up, you back up, back up, back up. And the next is, okay, you. Then the rest, back up, back up, back up. That is wireless communication. Right? It's not like wired network. Okay. So, so principle here in wireless communication is the collision avoidance. The method to make sure collision avoidance is to tell them wait. So if you, similar to cell communication also, a lot of weights, right? When you do Wi-Fi, let's say you have a Wi-Fi router at home. If you share your Wi-Fi router with 4 families, each family has 10 people. So 40 people using together. Then your wireless communications has a lot of weights. Weights that you can, at your side only you can see or you can complain. It is so slow. But internally, technically, they said, you wait, you wait, you wait. So a lot of idling, right? You see it at home, right? A lot of idling. Is it only my case? Maybe my case. Okay. And to do that, to this collision avoidance, this is the key things. Carrier sense. Carrier sense is important. Carrier has some sense. What is a carrier? Signal. Signal itself has some sense. But carrier sense is not really always robust, right? But anyway, carrier sense takes a while to switch between TX and RX, transmission and receive. Transmit and receive. Wireless is not perfect broadcast because it is a transmission and transmit and receive. So the components in wireless Wi-Fi, there's a station. So station has basic service set. BSS. There is a service set ID, right? SSID, for example. SSID is usually at home when you have a wireless router, then that is the ID of your wireless router. That is SSID, service set ID. Okay. And there is an extended service set. If we have, for example, access points and tracking mobility and distribution systems. So what happens here is that this is you have server, for example, yeah, our say web server, database server. From there, through some LAN communication, you have distribution systems, and it reach to the access points. From these access points, then you have station, multiple stations. They all are using the same SSID, right? This guy, all the station here is accessing this access point, station ID, I mean service set ID. Yeah, multi Wi-Fi, that is a service set ID. At home, you have something that you name, or if you subscribe to Amazon.com, then they already give you, right? They set up service set ID and you simply use it. If you subscribe to another cable vision, then I think you can set up, right? You can name it. You can define ID. I mean, regular router that you purchase, then first setting is the SSID. It may not ask you to enter SSID, but it may ask you name of your network. Then you can say Yun's Home Wireless. Then that is the SSID. So you have one, say, for one access point, you have a multiple station. Another access point, you have another multiple stations. Some station here, some station, for example, some of your laptop has Zigbee, right? Zigbee. This Zigbee is talked to another Zigbee where there is an Arduino Uno, Arduino Mega, or Raspberry Pi, or Beagle Bones. There's so many others, right? So these are all in the category, the technique of a Wi-Fi. So we looked at that. Basic service cell is a cell. PSS set of stations associated with one AP access points. Distributed systems, extended service set, independent basic service set, IBSS, set of computers in ad hoc mode as independent. For example, if you have a multiple Zigbees, they are talking each other, and one of them, a few of them, can talk to the station, which is associated with one access points. Ad hoc network coexist and interoperate with infrastructure based or infrastructure based network. Back here. Okay. So Mac has the IEEE 802.11 has a max of layer, and Mac management protocols, and physical layer. Physical layer, maybe infrared frequency. What are these two? We looked at last week. It stands for FHSS and DSSS. Frequency, hopping, spread spectrum, DSSS, direct sequences spread spectrum, right? We did the exercise. Oh, I'm going to make next homework one from that DSSS, well, CDMA coding. That's what we did last time, and also for encoding Manchester or things like that. Okay, one homework of two different questions. Original 802.11 was at 1 megabps, 2 megabps. Now it goes up to 200 megabps, more and more. Huh? Oh, that yeah, version of Wi-Fi 11A, 11 yeah G. That's right. The goal of 802.11 is to deliver services in wired networks, wireless networks, should be wireless network, to achieve a high throughput, to achieve a highly reliable data delivery, to achieve continuous network connections, so wireless. Services that we can think. See, we have station and distribution services, which is, you can simply say AP, access points. Services from AP and services from your laptop. Okay, say laptop. Access points first distribute saying, hey, I am here. I am here. I am here. I am here. Then you need to send, oh, I want to talk to you. So get some authentication. And then this guy said, okay, we can association. And this AP says, get out of here. If you are kicked out from Wi-Fi, then you have to re-authentication. Well, sometimes, many times, right? Even if you turn on, then from time to time, you can be off from that wireless access points communications. Then you have to re-associate, re-authentication, right? That if re-authentication is requested, then a re-association. Integration between your wireless and wired communication can be integrated by access points. Oh, this is good. This is a good example. After this example, then we will stop. Okay. So we have a cell tower. You don't have to say there is a cell tower. Simply access point. So we have 3 access points: access point 1, access point 2, and access point 3. Now you are driving while you are working on your laptop. So this is your laptop. You drive in this path. So first you have to do A here. A, station finds AP1, which means how this guy finds AP1, because AP1 already distributes. Hey, I am here. I'm the access points. I'm ready to serve you. Then station 1, oh, I found. And let's do authentication. Authenticate. If it is if it is okay, then this AP1 says, okay, associates. And traverse. B, so station moves. It may pre-authenticate with AP2. So pre-authenticate. Try get some authentication because he's getting away from access point 1, and this guy already got message from AP2, like distribution messages, so get some pre-authenticates. And when the association with the AP1 is no longer desirable, see here it moves. So this is far from there, then it may reassociate with AP2 because already authenticated, therefore associate. And then D, so access point 2 notify to access point 1. Hey, you terminate of sending data to the station that I am currently associating. Then access point 1 is completely knocked off from this scenario. And then here, it moves further. So at some points, AP2 may be taken out of service. AP2 would disassociate the associated station. If this guy approaches further to access point 3, then disassociate, and then this guy will finally associate. If you look at the services that we looked at here, at this scenario, then authentication, association, pre-association, reassociation, disassociation, and authentication, and association. So repetition of such. That is a service. if you look at the Wi-Fi, if you look at the Wi-Fi through Wireshark from the beginning, then you can see some of the packets associate, some of the packets distribute, some of the packets authentication. You have to find out clearly. But usually you cannot because your laptop does not provide the access points. So our Tech Nights, that is somewhere here available, software access points. There are two types of access points, right? Hardware and software. But if you have a hardware access points, then you cannot set up the Wireshark there. Therefore, better set up software access points on your laptop. So one laptop set up access points running Wireshark, another laptop just running Wireshark, and the other, the laptop with the no access point is the station. Laptop with the access points, that is the distribution center. And both runs Wireshark, so that you can see the packets clearly. Okay? Question? No question? Get some idea, right? Okay. Have a good night. Woo!